Hi dear students, we are at unit number 2, Eigenvalues and Eigenvectors, lecture number 2. So in the last class, lecture number 1, I have given one exercise, problem number 3. Hope you have done. Just let T from V3 over R to V2 over R is defined by T of x comma y comma z is equal to modulus of x comma 0. So this problem, is it a linear transformation or not? Okay. So let me. So first, to verify this one is a linear transformation or not, we need to verify this T has to satisfy two conditions. So first one is it should be closed under addition, addition, and it should be closed under scalar multiplication. Okay. So first condition, it has to satisfy T of two vectors we need to take A bar plus B bar should be equivalent to T of A bar plus T of B bar. Okay. And second condition, it has to satisfy T of C times A bar. C is a scalar, so scalar will comes out like this. So here A bar comma B bar, they are coming from the domain U. U is a vector space, and C is coming from field complex number set. Okay, let's verify one by one. So first, before verifying this first condition, we wanted two vectors from the domain V3 over R. Okay, so let us take two vectors. I am taking first vector A bar is some A1, A2, A3 because it is three-dimensional vector. So it belongs to domain U. Similarly, B bar, two vectors I am taking B bar, which is some B1, B2, B3. Okay, and this is also belongs to the domain U. Now we need to verify T of A bar plus B bar. So this is LHS part. First let us compute LHS part. Okay, I am computing LHS part first. Okay, LHS part. So this is T of what is A bar? A bar is A1, A2, A3. Okay, next plus B bar. So B bar is B1, B2, B3, three-dimensional vector. Okay, then do the coordinate wise addition. T of A1 plus B1, right? First coordination adding to first coordination, and A2 plus B2. This is how vector addition is defined. And A3 plus B3. You know how to add two vectors from your PUC. So now again same, it is three-dimensional vector only. A1 plus B1 is one component, A2 plus B2 is second component. Okay, so this is one component, A1 plus B1, A2 plus B2 is second component, A3 plus B3 is third component. Again this vector is again belongs to U only, domain only, right? This belongs to U, but this T of this entire thing will belongs to V because it is codomain vector, T of this entire thing. Okay, this is image actually. So this is domain entry and T of this one is codomain entry. So now according to definition, what is this T of x comma y comma z is equal to modulus of x comma 0. That means first component become modulus and next one is 0. This is codomain entry. Codomain is V2 over R. That's why it is a two-dimensional vector. So similarly, according to definition, this one is modulus of A1 plus B1, first component, comma 0. This is according to definition of the function or map T. Next, let us look at RHS part. Okay, in RHS part, again, so here T of what I want? C times, okay, so T of A bar I need to compute, T of A bar, T of A bar. So T of, what is A bar? A1, A2, A3. Okay, So a1, a2, a3. So this is T of the vector. According to definition, again this is modulus of a1 comma 0 by definition, because map is defined like that. Okay. And similarly, what is T of b bar? T of b bar is same. Okay. So T of what is b? The vector b is b1, b2, b3. Okay. So which is modulus of b1 according to definition of the map, modulus of b1 comma 0. T of b bar is this. Okay. Now from these two, so T of a bar plus T of b bar I want, that is RHS value. So T of a bar plus T of b bar. This value I want actually, T of b bar. What is this? So which is modulus of a1 comma 0 plus modulus of b1 comma 0, isn't it? Look at here, this one and this one I'm adding. Okay, T of a bar plus T of b bar, and this is equivalent to modulus of a1, again coordinate wise addition, plus modulus of b1 comma 0 plus 0 is 0 only. I'm adding these two vectors. Okay, and assume this is number 2. Does 1 is equal to 2? See, look at modulus of, since modulus of a1 plus b1 is not equals to modulus of a1 plus modulus of b1, right? This is not equals to. That's why equation number 1 is not equal to equation number 2. Therefore, it is not a linear transformation, clearly. So how this is not equal? Actually, it is triangular inequality, right? This is actually less than or equals to this one. Let us verify one example. For example, let us take 5 or minus 5 plus 3 you take. Okay, minus 5 plus 3, where minus 5 is a1 and 3 is b1. Okay, and what is this? Is it so? This one we need to verify whether it is equivalent to or less than or equals to. So modulus of minus 5 plus modulus of 3, isn't it? But what is this? Modulus of minus 2, modulus of minus 2. What about this? And this is 5 plus 3, isn't it? 5 plus 3. This is 2, 8, which is, so this is more than that. So therefore conclusion is, this is just for understanding purpose. So therefore conclusion, so no need to verify the second condition. First condition itself is not satisfying. So therefore the given map is, or simply therefore from 1 and 2, from equation number 1 and 2, what we can say, 1 is not equivalent to 2. So therefore the map is not a linear transformation, not a LT. LT means linear transformation. That's it. It's not a linear transformation. Okay. And in the last class we discussed first problem as some excess T of AB, like let me write here. Since the concept is linear transformation, okay, in the last class we discussed the map is like this. T of some a comma b is what you written, a square plus b square kind of. You remember a square plus b square. Look at you're supposed to verify does it a linear transformation or not. So without verifying, without going into calculations, I can say this is not a linear transformation. How? Because the word linear I am using here, it is transforming to linearly, linear transformation, right? Transforming linearly, but it is transforming non-linearly. Look at this, a square plus b square is non-linear terms because their degree is not equals to 1. Look at a power is 2, b power is 2. If it is just a plus b, then find it is a linear transformation. But it is not a plus b, it is a square plus b square, so non-linear terms. So straight away I can say that this is not a linear transformation. This is a rough idea about linear transformation. Similarly, you look at for this problem, modulus of x is not a linear term. Again, this is non-linear term only. So that's why this map is not a linear transformation. Clear? Next one. Some geometrical aspect of eigenvalues and eigenvectors. So the geometrical view. Okay. So in the last class, we discussed one problem about 1 0 oh sorry 0 1 0 1 1 0. For this matrix, we guessed what are the eigenvectors, right, and what are the eigenvalues we guessed, right, in the last class. So what is meant by x's and lambdas in geometrically? Okay, let me take one more in the problem. One, let us consider a 2 by 2 matrix 1 4 3 2. Consider this matrix. Now this is a matrix A, and find out what is eigenvector such that what is that ax is equal to lambda x, right, according to the definition of eigenvalues and eigenvectors. So such kind of x we need to pick up. So those are called eigenvectors. So lambda, so what is lambda into x? So lambda also question mark, right? This is also question mark actually. What are lambdas and x's? So roughly, let us choose. So 1 4. So we need to keep on search. Of course, searching is very difficult, but in this class only I will tell you the technique how to find lambdas and x's, eigenvalues and eigenvectors. But before that, this is a mechanism actually. It's a general mechanism. Okay. So now here I am searching uh, what is such x such that ax becomes some values of lambda into x. So let me write this one is some let me write 1 1. If it is 1 1, then what is the computations? 1 1s are 1, 4 1s are 4, so 5, and 3 1s are 3, 2 1s are so 5. So 5 comma 5, so 5 5 I am getting. So this 5 5 I can write 5 is out 1 1. Can I write 1 1 like this? So it's like again same lambda x bar kind of. Look at, I started with the same x. This is x bar, right? X bar is 1 1, x bar is 1 1, same only. So now you end up with the requirement. So ax bar is equal to lambda x. Therefore here I can say that, so this phi is called eigenvalue, and this 1 comma 1 is called eigenvector, right? So this phi is called eigenvalue, and this is eigenvector. Okay. So I said in the last class, so I am collecting the vectors such that ax bar is parallel to x bar, right? So based on this, we are collecting what are the eigenvectors. Ax bar is parallel to x bar, so in that sense I am getting ax bar is equal to some lambda x. So that is a definition actually, because they are parallel, some constant will differ, therefore lambda into x bar, isn't it? So now if you look at geometrically, right? Ah. So ax bar and x bar, they are parallel. So first let us draw what is x bar. Okay, here what is x bar in this problem? X bar is 1 1. So if this is 1 and if this is 1, and 1 comma 1 should be here, right? So this is 1 comma 1. So therefore with respect to origin, so this is the vector, and what is this? This is x bar, isn't it? This is x bar. So x bar is over. Now I need to draw the what is ax bar. What is ax bar now? Ax bar is 5 5, right? Compute ax bar value is 5 comma 5. 5 comma 5 means somewhere, assume this is some 5. So this is some 5, and assume this is some another on the y-axis, right? On the y-axis. So this is 5. This is 5. So then corresponding value this. So this is 5 comma 5. Then again draw this same only, right? So this will be same. So this is 5 5. So this is Ax bar, right? This is Ax bar. This is Ax bar. This is X bar. This is Ax bar, isn't it? So therefore, what you understood here? Indirectly, Ax bar and X bar, they are parallel, right? Parallel means they can be on the same line, or they will be like this, or they are coinciding, like they are parallel only. What do you mean by parallel? Their angle between the two vectors must be 0 degrees, right? So here angle is 0 degrees. There is no such angle. For example, if this is one vector A bar and this is another vector B bar, then they are making some angle. This is theta. Okay, but here they are not making any angle, these two. So therefore angle is 0. Angle is 0. Here also they are not making any angle. They are coinciding means again angle is 0. Such vectors are said to be parallel. So this is a geometrical view of eigenvectors, and corresponding values are said to be eigenvalues. What does it mean by geometrical view of eigenvalue? Old vector x bar, look at here in the graph, old vector x bar, now after transformation, after linear transformation, it became ax bar. So here a is like a function t, transforming the vector x bar to ax bar. Understood? So x bar is a domain vector, t it is like a t, so transforming x bar as a lambda times x bar. So how you are getting your a times x bar, right? So now the geometrical view of lambda is nothing but stretching 5 units. So this is old vector, x bar is a old vector. Now after transforming, you are getting this ax bar. Ax bar is nothing but 5 times old vector. So this is nothing but ax bar is similarly equal to 5 times x bar, right? Yes or no? Stretching 5 times. So now lambda means here stretching. The geometrical view of lambda meaning is stretching, kind of stretching or shrinking. Stretching. Sometimes it may shrink. It may shrink means, like for example, if this is the x bar, if this is the x bar, after transforming you may get like this, which is half times x bar. That means half times it is shrinking, right? Half times shrinking. That means, so now this is ax bar. This is ax bar. Clear? Shrinking now. It is shrinking. So therefore here geometrical meaning of lambda is nothing but stretching or shrinking factor. Lambda is. Okay. So this is geometrical aspect of what are eigenvalues and what are eigenvectors. Next, let us compute eigenvalues and eigenvectors. So already we have seen how difficult it is guessing work of x's and lambdas, guessing work of eigenvalues and eigenvectors. It is not so easy always. So let us learn a proper mechanism to find eigenvectors corresponding to the eigenvalues. Here I will explain the mechanism. Okay. So let A be an n by n matrix. So first I am taking a square matrix. Okay. Why I am taking square, you will get into know. First A be an n by n matrix with eigenvalues or eigenvectors x bar corresponding to the eigenvalues corresponding to the eigenvalues. What are the eigenvalues? Lambdas. Okay. So then clearly, so what we can write, x is equals to lambda x. Why? Because x's are eigenvectors and lambdas are eigenvalues. I have taken itself in the assumption. So therefore, clearly you can write ax is equal to lambda x. Okay, these are eigenvalues and eigenvectors of matrix A here. So then we can build up this equation. So now listen carefully each and every step. So now can I write Ax minus lambda x equal to 0? Does it correct? So this is wrong. Can you guess why? Because lambda is a number, isn't it? Lambda is a number. Is it right or wrong? Wrong. Why? Because okay, lambda is a number, x bar is a vector. So now a vector means the matrix representation. We will get a matrix here. So finally, lambda x is a matrix. Fine. A is a matrix, x is a matrix. So product of two matrices is again matrix. Matrix minus matrices makes sense. But I am saying I am telling this is zero, but this is not zero. This is null matrix. You have to say. Okay, it is not zero. It is null matrix. Matrix should be equivalent to matrix only, right? As I said in my doubt session, 2 liters, 2 liters, they never equals to 2 kilometers, right? Because here the units are different. Here liters, here kilometers. How they are equal? Same kind of here. So these left hand side is matrix, but right hand side is number. How matrix equal to number? Can I write? It does not make sense, right? 1, 2, 5, 6. I cannot write it is some number 7. It is nonsense, right? Matrix should be equivalent to another matrix only. Same like this. 2 liters is not equivalent to 2 kilometers kind of. So instead of saying this is 0, you say null matrix. Pronunciation is important. Clear? Okay. Now it's a null matrix. Fine. Next step. Can I take x is common? A minus lambda into x. Does it correct? Is equal to null matrix. Is it correct? This is wrong again. I'm saying, listen once again. A matrix A minus lambda into x is equal to null matrix. Though it is wrong. Why? Because A is a matrix, lambda is a number. So matrix minus number not make sense. Same like this. Look at matrix is equal to number, matrix minus number is not make sense. Then what we did wrong in this? Nothing we did. It is okay. This step is okay. Here just x we have taken common. So I am making the step make sense. How it makes sense? Just a simple modification. So instead of taking directly x common, let me do one more step to make it make sense. To make it make sense, what I am doing is a into x, clear, minus lambda into x is any matrix. So can I write that is I into x? I is identity matrix. Identity matrix into x is again x itself. Okay. Why I'm writing like this? Because I want to make this step make sense. Just now I told you already. So now identity matrix into x is x itself. Now you go to the previous step. Lambda into x will get no problem. Now you can take common x. So now a minus lambda into I, identity matrix, into x is equal to 0. Now this step is makes sense. Look at a minus matrix minus matrix only. Lambda is a number, I is a matrix. Lambda into I is again matrix. So matrix minus matrix is makes sense now. Now this is meaningful. Okay, this is meaningful now. So it is very clear. Next, our goal is, what is our goal? Our goal is to compute eigenvalues and eigenvectors. I need to find out what are lambdas and what are x. These two unknowns we need to calculate. Two unknowns means here x I want to find, lambda I want to find. Okay. First let us concentrate on this x. Okay. See, if a system of equations are given to you, first what we will do, we will write as a matrix representation. A into x is equal to some b kind of, right? Isn't it? So A is a coefficient matrix, x is a variable matrix, b is a constant matrix. This is a matrix representation of system of linear equations. But what is x here? X is, for example, three system of linear equations are given with three unknowns. Then, for example, x1, x2, x3 unknown. So here solving the system of linear equations means indirectly we need to find what is x1, x2, x3. Indirectly we need to find what is x, right? Our main goal is to find unknown. Unknown here is x in system of linear equations. Clear? So for that we are struggling what is x1, x2, x3. Indirectly we are finding what is x. Same kind of here. Now this is like one matrix. A is a matrix, lambda into I is another matrix. Matrix minus matrix means you will get one matrix. Let's say it is some B, matrix B. B into x is equal to some 0. Same like this only. Look at A into x is equal to B. This B not same. Let's write this the different notation. Okay. Let's write this is some matrix D. Okay. D into x. Matrix D into x. It's look like same only. So instead of A you are having D. Now this D is a coefficient matrix. So this D is coefficient matrix. It is coefficient matrix. Okay. Coefficient matrix. Okay. And what about x? X is variable matrix, right? X is variable matrix, and this is coefficient matrix. Coefficient matrix, and this one x is variable matrix. Variable matrix. Okay. And what about this? This one is null matrix. It is not zero. Null matrix. So null matrix, which is constant matrix. And this one represents system of linear equations, constant matrix. Okay, system of linear equations. So clearly, so again, this represents a system of linear equations. Particularly, this is null matrix. Null matrix means all are zeros in the entries. All the entries are zeros. Therefore, it's called homogeneous system of linear equations. Homogeneous means if the constants are zeros, this is called homogeneous system of linear equations. Okay, homogeneous system of linear equations. Okay, this why? Because here 0 you are given, null matrix is given. That means, for example, 2x plus 3y is equal to 0. Just one example I am telling. And 3x minus 4y is equal to some 0. Look at the coefficient constant you are having 0 and 0 here, 0 and 0. That's why this is called system of homogeneous. These are system of homogeneous equations, homogeneous linear equations. Instead of 0, if you are having, like, for example, 2x plus 3y is equal to some 2 and 3x minus 4y is equal to some 5, 2 and 5, then this is called non-homogeneous. Okay, non-homogeneous system of linear equations. Non-homogeneous system of linear equations. Otherwise, it is called homogeneous system of linear equations if it is 0 0. Okay. Now here, since the constant matrix is a null matrix, therefore this is homogeneous system of linear equations. Clear? Now my goal is, what is this variable matrix x? Because x is here my eigenvector. I want to find what is x first. Okay. So now what I am doing is, look at clearly now. So d means what? A minus lambda into x, right? So let me write that as it is. A minus lambda, or let me write the dx, no problem. D into x is equal to null matrix. I think you heard the word singular and non-singular. I am using the word here singular and non-singular. Singular means what? Singular means what? Det should be 0. Determinant. Det is 0, right? Determinant is 0. That is called singular. Non-singular means non-singular. Determinant is not equal to 0. That is called non-singular. Okay. Det is not equal to 0. That is called non-singular. So here I want to use that concept I want to use, singularity and non-singularity. So what I am doing is, here, look at both sides. I want to multiply with D inverse. Assume D is non-singular. If D is non-singular means what? Determinant exists. If D is non-singular, then I can multiply both sides with D inverse, because inverse exists. D inverse into D into x is equal to D inverse into null matrix. Okay, but this is D inverse into D identity matrix. Identity matrix into X is X itself, right? And D inverse into 0, this is null matrix. D inverse into null matrix. So multiply any matrix with null matrix, you will get 0, provided this multiplication is possible. That means it satisfies the number of columns in D inverse is must be equals to number of rows in null matrix, such kind of. But what you got here, null matrix is 0. So it is not just is trivial solution. It is not importance in this 0 vector is not importance here. We want some non-zero vectors x bar. Okay. See, obviously, if you look at this equation, first equation, ax is equal to lambda x. If I substitute x is equal to null matrix, a into 0, lambda, a into null matrix is equal to lambda into null matrix. Obviously, they will satisfy. Null matrix is equal to null matrix. This is not interesting, right? This is not interesting. Obviously, substitute here x is null matrix here. And here also x is null matrix here. What will you get? A into whatever the matrix A you take, that matrix into null matrix. How much? Null matrix only. And lambda, whatever the number you take into null matrix, again we will get null matrix only. So null matrix is null matrix, satisfying. So there is no importance in that. Then let us find the non-zero vectors. Okay, non-zero. In the definition, you look at eigenvectors are non-zero vectors, right? So our focus is on to find the non-zero vectors. So therefore here, if D is non-singular, that's why I'm getting x is equal to 0. Therefore D should be singular matrix. D should not be non-singular. If D becomes non-singular, what happens? This kind of eigenvectors I will get. But this is not an eigenvector because eigenvectors are non-zero vectors. Look at the definition. So therefore D must be singular matrix. So therefore here what I can write? So therefore since eigenvectors are non-zero, so therefore D must be singular matrix. It should not be non-singular. Once it is non-singular, zero vector exists. Non-singular matrix. And now non-singular matrix means what? That is determinant of D is equal to 0. Once determinant of D is equal to 0, then what happens? D inverse does not exist, therefore you cannot multiply both sides. Actually, in general, what is the inverse of, for example, A is a matrix. How to find inverse of A? 1 by determinant of A into adjacent matrix, right? Already you have seen in PUC, adjacent matrix of that A. So in this context, if det is equal to 0, 1 by 0 infinity, right? So in A inverse does not exist. That's what I am telling. If det is equal to 0, determinant is equal to 0, then inverse of D does not exist. Clear? Look at here. If determinant of A is equal to 0, then how to find A inverse? So 1 by 0 because det is 0 into adjacent of A. Whatever adjacent of A, forget about it. But 1 by 0 you are getting infinity. So A inverse does not exist. So for singular matrices, inverse does not exist. For non-singular matrices only inverse exists. Clear? So now here D must be singular matrix and det is equal to 0. So once det is equal to 0, what is D? A minus lambda into I into x is equal to 0. So since D, which is A minus lambda I, is singular, once it is singular, then what kind of solutions exist? Then non-zero solutions exist, right? Non-zero solutions. Non-zero solutions means here eigenvectors only. Non-zero solutions x exist. What is x here? Eigenvector only, right? We want only non-zero eigenvectors only once it is singular. Okay, so that is, it is singular means what? Modulus of determinant of A minus lambda I equal to 0. Okay, then non-zero vectors are non-zero solutions, non-zero solutions exist. Okay, so our concentration is non-zero solutions, so that should be equivalent to 0, right? So here you look at In this equation is called, it is an equation. What is meant by equation? If it is equal to 0, it is called equation. Equal to something else. For example, 2x plus 3y, it is not equation. This is an expression, algebraic expression, right? This is an expression. It is not equation. Expression. What is equation? 2x plus 3y is equal to some 0, or 2x plus 3y is equal to some 5. So these are equations, algebraic equations. This is algebraic expression, these are equations. So now it is equal to 0 is there, therefore this entire thing is equation. Okay. So the above equation determinant of a minus lambda I equal to 0 is said to be characteristic equation. Characteristic equation. Characteristic equation. This equation, modulus of determinant of a minus lambda is equal to 0 is said to be characteristic equation. And here you look at the expression det of a minus lambda I, forget about equal to 0. Only this expression you look at. What do you get actually? A is a matrix. For example, A is a matrix. Let us call 1, 2, 3, 4. Just look at, assume this is A, matrix A. Okay. Minus lambda is some number. Let us call 3. Okay. And matrix 2 by 2 only have to take because A is 2 by 2. So 1, 0, 0, 1. Okay. So let us call this one itself lambda only, right? Don't take 3, lambda, because we don't know what is lambda. We need to find what is lambda. Now what do we get this one? 1 minus lambda, okay, 0 and 3 and 4 minus lambda, right? After simplify this. So minus lambda will become here. So it becomes lambda 0, 0 lambda, right? After multiplying with lambda, identity matrix. And now subtract this matrix from here. 1, 2, 3, 4 minus lambda 0, 0 lambda. You will get this matrix. And which is in determinant, right? So once it is in determinant, if you expand it, what you will get? 1 minus lambda into, isn't it? 4 minus lambda, right? Minus 0. If you expand it, you will get a second degree polynomial in lambda. Okay? Second degree polynomial in lambda. Therefore, if we expand determinant of a minus lambda I, we get an, which degree polynomial? Can you guess? What is the degree of this polynomial? Here, for example, 2 by 2 matrix I have taken, I am getting second degree polynomial. Look at. So, polynomial. Which degree polynomial? Can you guess? What is the order of A here? A order is, A is a matrix of order n by n. So, it is nth degree polynomial you get, right? At the beginning, I have taken A is n by n order matrix. Therefore, nth degree polynomial. Right? Nth degree polynomial. This polynomial is said to be, this polynomial is said to be nth degree polynomial in lambda, right? Okay. And this polynomial is said to be characteristic polynomial. Characteristic Same, it is characteristic equation, this characteristic polynomial. Characteristic polynomial. Okay. So clear. Now, so characteristic polynomial you're getting in lambdas. So that means equation in lambda you're getting. You solve that equation by a theory of equations in PUC 2. You know how to solve uh, more than second degree equations, right? So now this is characteristic polynomial. So you can solve this. You will get lambdas. So those lambdas are called eigenvalues. Those lambdas are eigenvalues. Okay, eigenvalues, and assume this is equation number 1 here. From 1 you will get eigenvectors. Eigenvectors by substituting lambdas. By substituting lambdas. Okay. So here from the last polynomial, characteristic polynomial, solve this from this characteristic equation. You will get characteristic equation in nth degree. So solve that equation. You will get eigenvalues. Take the eigenvalues one by one and substitute in this equation. Lambda is 1. Substitute here 1. And sorry, not this is 1. Yeah, because this is not 1. Take this one is, so this one in this one equation. This is equation, right? So in this substitute x value here, lambda value. So if you substitute lambda value here, you will get an equation in term in x only, right? So solve for x. Solve for x, you will get eigenvectors. So here two unknowns, isn't it? One is eigenvector and another one is eigenvalue. Let me do one problem quickly. Look at this. Find eigenvalues and eigenvectors of the matrix 3 by 3. Find the characteristic roots and the corresponding characteristic vectors of the matrix. So eigenvalues, eigenvectors are nothing but characteristic roots or characteristic vectors. Just now we have seen. Look at eigenvalues are nothing but characteristic vectors. They're same. Eigenvalues, characteristic roots. Sorry, eigenvectors, eigenvalues means characteristic roots. Eigenvectors means characteristic vectors. Another name. Okay, both are same. You can ask like this also. We need to find eigenvalues and eigenvectors, right? Now let's look at how to find eigenvalues and eigenvectors. Here are two things we need to find: lambdas and x's. First, lambdas eigenvalues. How to find eigenvalue? Let A is the given matrix. Okay, 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1 and 3. Okay, what is first one? What do we want? Eigenvalues we want, right? First, after that eigenvectors I will get. So eigenvalues. How to get eigenvalues are characteristic values. We need to write the characteristic equation, right? What is characteristic equation? So first one is we want eigenvalues first. After that eigenvectors. Yeah. So the characteristic equation of given A, given matrix A is, what is it? modulus of A minus lambda I 3 I am writing here because A is 3 by 3 matrix equal to 0. This is characteristic equation, and this alone is characteristic polynomial. Look at here, it is determinant of A minus lambda I3. This characteristic equation. So if you solve this characteristic equation, you will get eigenvalues, right? Just now we discussed already. Now let us come to this calculation. So first, so determinant of what is A? A is 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3. Okay, so this is A. Minus lambdas. Lambdas we don't know, we need to find that lambdas only. Lambda is unknown. And identity matrix 1, 0, 0, 3 by 3, right? 0, 1, 0 and 0, 0, 1. So this is 3 by 3 identity matrix. Determinant equal to 0. Okay, let me expand this. Yeah, let me expand this. First one, yeah, look at this one. First, let us simplify this. What will you get? So determinant of 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3. This is first matrix, matrix A. Okay, minus, let us take lambda inside. If we take lambda inside, what will we get? Lambda 0, 0, 0, lambda 0, 0, 0, lambda. Okay, and this is equal to 0. Det of this entire thing is 0. So matrix minus matrix, that's what I said. Lambda into I3 is a matrix, right? Matrix minus matrix makes sense. That's right. Next one, simplify this. So determinant of 6 minus lambda, first entry, 6 minus lambda, second entry minus 2 minus 0, so minus 2 only, and this is 2 only, and this is minus 2, 3 minus lambda, 3 minus lambda, and this is minus 1 only, and last entry this is 2, right? This is minus 1, but this is 3 minus lambda. This is det is equal to 0. You know how to find determinant. First I'm expanding to A11, so let me write this. So 6 minus lambda, 6 minus lambda into, yeah, multiply with this. So 3 minus lambda into 3 minus lambda, is it? So 3 minus lambda square, 3 minus lambda square. Okay, next minus 1, 1 into 1, 1. Next I'm finding determinant. Next minus 2 into, so minus into minus plus 2, because middle row, middle entry, I'm expanding the det with respect to middle column, so minus will come, right? So minus of minus plus 2. Next multiply minus 2 into 3 minus lambda, 3 minus lambda. Next, so this will go, right? So minus 2 into 3 minus lambda, and 2 into minus 1, so minus 2. Next, last 2, so 2 into this 2 into this one, minus 2 minus 1, so 2 minus 2 into 3 minus lambda, 2 into 3 minus lambda is equal to 0. Okay, now expand this. 6 minus lambda is outside, 6 minus lambda is outside, and inside, so lambda square, a square plus b square, right? So plus 9 minus 2ab, so minus of minus plus minus 2ab, so 6 minus 6 lambda, right? Isn't it? And minus 1 extra here, minus 1 extra, so minus 1, because here minus 1 is there. This is expansion of 3 minus lambda whole square over. Now let us simplify inside one. 2 inside factors, minus 6 plus 2 lambda minus 2, this one, minus 6 plus 2 lambda minus 2, and plus 2 into inside factor 2 minus 6 plus 2 lambda equal to 0. Okay, after that you simplify this term. Okay, yeah, let me write the next phase. Let me write again this equation as it is. 6 minus lambda into lambda square plus 9. So now let us simplify this more and more. So 6 minus lambda, okay, 6 minus lambda, yeah. So lambda square and minus 6 lambda, 9 minus 1 is plus 8, okay, 8 plus 2 into this one, 2 lambda minus 6 minus 2 minus 8, okay, plus 2 into, simplify this, 2 lambda minus 4. Make sure that everything is correct. Okay, minus 6 lambda plus 8 and 2 lambda minus 8 and 2 lambda minus 4. Yeah, let's expand this 6 into this. So 6 lambda square, multiplying with 6 first, minus 36 lambda. Okay, next plus 6 8 is a 48. Next expands through minus lambda. So minus lambda power 3, lambda raised 3, and plus 6 times lambda raised 2 and minus 8 times lambda, and here plus 4 times lambda, 6 lambda. Let me go back. Yeah, let me verify this determinant one. 6 minus lambda, so 3 minus lambda whole square, yeah, minus 1 and 2. Okay, and so 2 minus 2, so this is plus, right? Sorry, so this is plus. Look at, I am expanding through minus 2, so this will go minus 2 into 3 minus lambda, and minus 2 become plus 2, right? It is, so this is plus 2, and this become minus 6 minus 2 lambda plus 2. Okay, and in the next step this is plus 2, so this is plus 2, right? This is plus 2, so minus 6, so this is minus 4, isn't it? Minus 4, so minus 8, this is not 16, so minus 8, so this is minus 8, so 2 4 the minus 8, yeah, minus 32 equal to 0. Fine. So look at one mistake. If one mistake happens, entire problem will collapse, because different eigenvalues will get and different eigenvectors will get. Entire problem will collapse. Be careful. Okay. Okay, fine. So now you are getting a cubic equation here, third degree polynomial, third degree equation. So three roots exist here. Okay. How to find those three roots? Already you have seen in P2 how to solve this kind of equations. Horner method you can find by Horner method. I remember Horner method. So let me do. So first lambda cube coefficient is 1. Next lambda square coefficient we need to write it minus 12. Next lambda coefficient 36 and constant minus 32. All the coefficients you have to write in order. If for example lambda square is absent, then its coefficient 0, you have to write here 0. First lambda cube coefficient, next lambda square, lambda and constant, like this. So that is order. Just you recall from your P2 how to find the roots by using Horner method. So now we have to guess. So here it should be 0, it should be 1 initially, right? And let us guess one by one. First I am starting with 3. Does it working out or not? 3 ones are 3. And minus 12 plus 3, 9. 9 3s are 27. And it is 63. 63 is, so it is not becoming. So 3 3s are 9, 3 6 are 18, 189. So it is not becoming equal, right? It has to be equal, but it is not equal to 0. Therefore 3 is not a root. That is a sign, right? So then like this you keep on search. Okay, by using Horner method. Now 0. Let us try for 2. I'm trying for 2. Okay, sorry, 1. So this is 1 plus 0 is 1, right? We need to do addition, right? 1 plus 0 1. 2 ones are 2, so minus 10. Minus 10 twos are minus 20. So 16, 16 to the 32. So you are getting 0 perfectly fine. So therefore 2 is a root. So once 2 is a root, therefore I can write this is lambda minus 2, right? Because this equation in lambda is lambda minus 2. Lambda is equal to 2 is a root. Lambda minus 2 into this is lambda square coefficient. So 1 into lambda square, isn't it? Minus 10 into lambda plus 16 equal to 0. Now this is second degree equation. You are having the formula minus b plus or minus. I mean no need to search because you are having formula minus b square minus 4ac by 2a. 4ac by 2a like this. So by using this, let me write. So I am verifying only this. So b is 10. So minus 10. So 10 plus or minus square root of b square 2 2 1 2. Yeah. Now b square. What is the b square here? 100 minus 4ac 64. Okay. By 2 times a. That means 2 only. This is equivalent to what will get 10 plus or minus, that is root 36, that means 6 by 2. So if you take plus, you will get 16 by 2 8 comma, if you take minus 10 minus 6 4 4 by 2 2 8 comma 2 you are getting. So total roots are, so therefore I can write here is lambda minus 2 and lambda minus 2 into lambda minus 8 equal to 0. So therefore lambda 1 is equal to 2 comma lambda 2 is equal to 2, lambda 3 is equal to 8 are the eigenvalues. Look at 3 eigenvalues we got. 3 eigenvalues existing. Therefore, next one is we need to calculate what is eigenvectors, right? I think time is more. I will do this one in next class, but I will tell you how to do eigenvectors. Eigenvectors. Next one is eigenvectors. So, what is an equation ax is equal to lambda x? Okay. From this a minus lambda into I x equal to 0. So this is the equation. So in this equation we have to substitute back. Okay. In this equation, so in this equation, lambda values one by one you have to substitute. Here lambda value is lambda 1 lambda 2 are same, therefore only one value we can compute. Okay, just substitute lambda is 2. So next step, case 1, case 1, case 1, what I am taking, lambda 1 is equal to 2 I am taking eigenvalue. So with respect to this eigenvalue, what is eigenvector actually? Okay, so now, so then equation number 2 implies what I will get, lambda 1 is equal to, you have to substitute here. So a minus what is lambda value? 2. Eigenvalue is 2. Don't think that sir it is lambda, it is lambda 1. Think that it is eigenvalue, lambda value, right? Lambda values are 3. Lambda is 2, lambda is 2 and lambda is 3. 3 values exist because it is cubic equation. So a minus 2, I am substituting lambda value here in this equation number 2. 2 into I into x equal to 0. And we have to solve this one so that we will get corresponding eigenvectors. So this I will continue in next class because time is already over. So with this I will stop.